We're going to continue our study of exponents, and we're going to go into what's called exponential functions. Up to this point in your math studies, we've really only talked about linear functions. So a linear function is going to be where the rate of change is the same. Now, an exponential function is going to look very different as well. So here's an example of a linear function, and notice where the variable is. The variable is in the exponent position, which is why we call it an exponential function. So we're going to get into the details of this, but the first thing to understand is taking from things we know, such as a linear function, and how is it different in an exponential function. So here's an example where we have a table. Now, if we want to find the rate of change or the slope of this particular function, what we're going to do is take the change of the y values divided by the change of the x values. So in this case, the y values from 2 to 4, it changes by 2. From the same x values, the same pairs of x values, it changes by 1. So 2 divided by 1 is a slope of 2. We go from 4 to 6, that's a change of 2, and the x value changes by 1. So 2 divided by 1 is 2. And then we continue the pattern here. So because the ratio of the changes of y's to the changes of x's is the same, in this case it's 2, this is an example of a linear function. In this case, our equation would be 2x plus or minus our y-intercept. So in this case, if we remember, our y-intercept is when x equals 0, and in this case, y is equal to 2. So the equation would be y equals 2x plus 2. That would be our linear function. So there's a little bit of review from things we've studied in the past. Now, let's take a look at this. Now, exponential functions are where the rate of change is going to vary with each point. So notice how when I talked, it was 2 over 1, 2 over 1, 2 over 1. Watch what happens in this example here. So we're going to do the same thing. We're going to compare the y values, and we see this changes by 4. This changes by 1, so 4 divided by 1 is 4. Now, for this to be linear, the next set of values all have to divide and simplify or reduce to 4 over 1. If it doesn't, it's not linear. So in this case, what we have here is we go from 8 to 16. That's a positive 8. To keep this linear to a value of 4, this would have to change by 2, and it doesn't. It changes by 1. So now we go from 4 over 1 to 8 over 1. All right. Well, let's look here. 16 to 32, that increased by 16, and this only increased by 1. And so you see that the values of y are changing in a value that's a power, okay? And we'll get into how to describe this type of function. So we can definitely tell this is not linear, again, because the rates of change are not the same. All right, so the next type of question. So first question, can you identify a linear function versus an exponential? Right, we just went over that given tables. The next type of question you're gonna have is evaluating this thing. This is where we just plug in a value for our variables. So in this case, we have negative 2 times 5 to the power of x, and we want x equaling to 3. So what do? We just plug 3 in for x, and then use our PEMDAS, our parentheses, exponents, multiplication, division, addition, and subtraction if we need it. Okay, so in this case, we have y equals, we plug our value of 3. 5 to the third power, this might be something you guys know. If not, you do want to study your cubes because they do come in often in problems. If not, use your calculator. 5 to the third power is 125 times a negative 2. So that's where the negative 2 comes from, and we get to negative 250. And I know it seems kind of odd how these numbers would end up that way, but that's the power of an exponent function. That's the strength of it. When you have an exponent, it really amplifies the values of numbers that you have. All right, so that's an example of evaluating functions. You literally just plug in, okay? We would do the power, right? Because that's our PEMDAS, our P, our exponent, our parenthesis. And then we're gonna multiply, and then we get our final answer, okay? All right, now one thing we talked about in the past with linear functions is the graph. What happens, where does it cross? Now, there's 2 components to the equation. We have the a, so in this case, the a in our example was negative 2. we have our b, and then actually the third component is the exponent. Now, what's going to happen is we're not going to be given the x, so the two values we're given are the a and the b. Okay, so if we look here in this example, there's two criteria. In this case, what happens when b is greater than 1? Okay, and notice it doesn't say equal to, it says greater than 1, so that's 1.0001, or those types of numbers. All right, so if a is positive and b is greater than 1, we're going to get a graph that continues upwards like so. If a is a negative value, okay, like the one we had in the other problem, the value would end up going down. All right, notice too where the y-intercept is. The y-intercept is going to be 0 and then whatever the a value is. Okay, and that's because whenever x is 0, it makes this 1. And then a times 1 is just a. Okay, so keep that in mind. So these are important here, and we notice that they're the same this way. So keep that in mind, what the y-intercept is of the graph, because also you're going to notice that's going to help us determine the direction. If you know the y-intercept and you know the general shape of the graph, then you know what direction the graph is going to go. Now, if you notice here, this graph never crosses the x-axis. Never does. It continues on forever, and it gets increasingly closer to the x-axis, but it never actually crosses it. Okay, and the same thing for the upper graph. It continues all the way out, but it never actually crosses the x-axis. Okay, now let's go to this one. In this case, we have b, which is going to be a decimal value, or some value, I don't want to say decimal, but a value less than 1, which often includes our common decimals, right? Or even our common fractions, such as half, a third, 2/3, 3/4, and so on. All right, now what happens to the graph is that it increases in the opposite direction. So if our value of b is a large value, it's going to increase in a large direction, this way, in a positive direction. If our value is small, it's actually going backwards and increasing this way, right? So in a situation like this is where something is big and eventually it gets smaller over time. All right, now down here, we have a negative a value, okay? But this time our b is going to be less than 1, but greater than 0, and so it's going to increase but never touch. Again, the same behavior at the x-axis is going to happen as it did over here. Okay, so that's understanding the graph shape. So use this as a template as you go through different examples and evaluate what's happening at the ends of the graphs. All right, so the next thing we're going to talk about is understanding domain and range, and we've talked about that in the past. Domain is going to be your input values, and range is going to be your output values. Okay, so what are the values for domain in an exponential function? What can we enter in? Well, we can enter in every real number possible. We can put any number in for x that we know of, and it will give us a value. Okay, so we could put in 1,000,000 for x. Now, even though it's way over there, 1,000,000 for x is going to make this thing extremely large. You can see because already at a value of 2, it's at 16. So if you put a value in of 1,000,000, it's going to get very, very large. Okay, so domain, all real numbers for any exponential function, not just this one, for any of them. Okay, now the range. In this example, the range is going to be greater than 0. And again, remember in the last example, I talked about how the graph goes on and on forever. It gets increasingly closer to the x-axis, but it never crosses it. Okay, so we cannot equal the 0, but it'll be greater than 0 in this case, right? And that is because of our a and b values, right? So if we look back here, let's go back to these examples. The domain and range, we just did this graph right here. What would the domain and range be for this? Well, the domain is all real numbers. The range would be y less than 0. So if this is y equals 0, because it is, it's any value less than that is going to be our graph, our range, okay? All right, now over here, our domain would be all real numbers again, and our range would be y is greater than 0, okay? And then for this one here, our domain is all real numbers, and our range will be y is less than 0. So notice what happens here with the a and the y value, right? Like if it's above or below. So if a is positive, our range is going to be greater than 0. Okay, so you can almost interchange the a and y for the range. So this tells you, okay, if a is positive, we're going up. Well, if a is positive, then the range is going to be greater than 0. Same thing over here, right? A is positive, our range is greater than 0. Down here, a is negative, so our range will be less than 0. It'll be lower. So that's a way to try to remember, if it's positive or negative if you're not given the graph. Okay, so there's a lot of information. I recommend you come back, write down some things, make some charts and tables to kind of organize this information so that you can remember this as you attempt problems in this section.